So let's look at a few basic transfer functions and what the Bode plots of them look like. So let's start with the first one. Let's see, Ts is S. It's really simple, right? So in this case, the function t j omega is just omega. It's equal j omega. So therefore, the gain function, and we are talking about in dB always when we talk about the Bode plots. And by the way, dB means decibel. And 1 bell, this is named after Bell, Alexander Bell. So the decibel is based on 10th of bell, right? So that's the unit. And so in this case, this dB is just equal 20 log base 10 of takes the amplitude of j omega. So the frequency we always make it positive, right? So in this case, I don't need to carry this absolute sign, so the j is dropped after we take the absolute magnitude, right? So in this case, the gain plot looks like quite straightforward, since the omega axis in let's see, the omega axis. So when omega equal to 1, the tj. So in this case, we are drawing the Bode plot, the gain plot for Ts equal to S. So in this case, when omega equal to 1, we have 0, right? So this is, let's say, this is 0 dB, this is 20 dB, this is 40 dB, and very typically we label the vertical axis in the division of the 20 ticks, and so we have negative 40, so on and so forth. So when omega equal to 10, so this is going to be equal to 20. So this is the 1. So this is 10. So 10, I have 20 here. And when this is 1.1 or 1 over 10, and I get negative 20. So this is really a straight line, right? So this is really a very straight line. So this straight line has 20 dB per 10 times the frequency we call the decade. So 1 decade, it means or denotes the frequency range of 10 times. Okay, so that's the very simple, right? Let's look at the phase plot. So the phase plot theta omega, we're just looking at that before. So in that case, theta omega is equal to the angle of t j omega, which is the angle of j omega, and that's equal 90 degrees. So in this case, if you plot this phase plot, that's just a constant, right? So I mean, you can label your omega, you have 1.1, 10. So the horizontal axis in the log scale. And in this case, you just draw a straight line here. So this is 90 degrees. And I'm drawing here the theta omega. So this is really very simple, right? So let's look at another one, slightly more interesting, hopefully. So in this case, we're looking at a Ts equal S over omega C. Omega C we call the cutoff frequency, or you can just think about it as a constant. Okay, cutoff frequency is just a real number, right? So in this case, the Tj omega is going to be equal j omega over omega C, right? So in this case, if we look at the plot, so in this case, when omega is equal omega C, in this case, the Tj omega dB is going to be equal 20 log of j times omega c over omega c. That's equal 20 log of 1. That's equal 0. Right? So that's 0. So this gain function crosses 0 dB line at omega equal to omega c. Right? So let's see if we have a more concrete transfer function. Let's just use, maybe use s over, let's see, s, we're using j omega over, let's see, the omega c is 100. So we are plotting this one. So in this case, when this omega equal to omega c, in this case 100 radian per second, the unit for this typically is 100 radian per second, and that's 0 dB, right? So if you have a 10 times that frequency, so in this case you have a 10 times the frequency, you have, let's see, 1,000 radian per second, and so in this case you got a 20 dB here, right? Let me move this down a little. So let's see, this is 20 and this is 0, and you got negative 20. So when, let's see, you have 10 and you got a negative 20, right? So therefore this, again, another straight line, but now the difference is you're not crossing the 0 dB line at 1 radian per second. Instead, you're crossing this at omega c, okay? So you still have 20 dB per decade, the slope, right? The slope doesn't change. And if we look at the phase plot, theta omega is still equal to 90 degrees. So I'm not gonna plot that, right? Okay, let's look at another one. So now you can think about the s over omega c s has 0 at the origin, right? So let's see if we have another transfer function at the pole at the origin, which is equal, let's say, omega c over s. So in this case, the tj omega is going to be equal omega c over j omega, right? So therefore, the gain function tj omega in dB, that's equal to 20 log of the omega c over j omega, and that's going to be equal 20 log base 10. We are always using base 10. So in this case, that's equal omega c over omega, right? So in this case, when omega is equal to, let's see, omega equal to, let's just maybe write a table here. So omega here, and we tabulate the dB here. So omega equal omega c, but that's equal 0, right? Omega equal 10 times omega c. So in that case, that's log 0.1, right? So that's negative 20. And omega equal 0.1, 10 times less, 0.1 times omega c. And that actually is equal 20 log 10. 20 log 10 is 1 times 20. So therefore, in that case, we got 20 dB. So in this case, we can draw the straight line here. And in this case, this is the omega c over j omega, this dB. And the horizontal axis is omega. And at omega c, this frequency, this is 0 dB, right? So at 10 times the frequency, 10 times omega c, 10 times omega c, we got negative 20, right? So let's see, this is negative 20, and we got a positive 20 also, positive 20 and 0.1 omega c, right? at 0.1 omega c. So therefore you get a line, you can draw a straight line in this case. Let's see if I can draw the straight line. So the straight line here is, this straight line has negative 20 dB per decade, and across this 0 dB line at omega equal to omega c. And this one here, remember this has the pole at the origin, right? So in this case, the theta omega is equal to the tj omega, the angle, which is equal to the 1 over equal to the angle of omega c over j omega. So in this case, omega c and omega are positive numbers. They are positive real numbers. So basically, you're taking the angle of 1 over j. Remember, 1 over j is equal to negative j. And you can do this by multiplying j on the numerator and denominator. So the numerator, the denominator now becomes j squared, which is negative 1, right? Negative 1. So in this case, this is equal to e to negative 90 degrees. Okay. So that's the that's for this one here is constant negative 90 degrees. So if you plot the phase angle theta omega, in this case theta omega would be, I should put here, and so this is the omega, and this gonna, you have a straight line at negative 90 degrees. Okay, so this pole gives you the negative 90 degrees. The pole at origin and the 0 at origin give you a positive 90 degrees, which is pretty straightforward. Okay, so these are in these three different cases, we don't really need any approximation, right? The next one we need approximation. Okay, let's start a new clip and see you in a moment.